All right, guys. So yesterday we had our quick introduction to torque. We defined the formula first. We said that torque was the Greek letter tau, and that's going to be R, which is our lever arm, times F, which is the magnitude of the force, times sine of the angle between them. Again, really important. This theta is not just any theta. It is specifically a theta that relates to the lever arm R and the force F. It's the angle between those two quantities. And these two things, R and F, are both going to be magnitudes. You don't have to worry about whether or not the forces or the distance vectors are pointing up or down or left or right. You don't include any signs for the R or the F. They're simply magnitudes. They're always going to be absolute values. What's going to give us direction is going to come a little bit later when we deal with the right-hand rule. Again, this R quantity here is called our lever arm, and if we remember from yesterday, that's the distance between the axis of rotation and where the force is going to be applied. We also defined something called the line of action yesterday. Look back at your notes, but it's just a line that goes through the force. Not a big deal. I think what would be useful is to see a couple examples to calculate the torque in a couple different situations. And then we're going to see how we can use our knowledge, our understanding of Newton's laws and forces back from chapter 4 to help us do some stuff here in chapter 7 with torques. I mean, we talked about how torques are the rotational versions of forces. So we're going to see if we can take a lot of our previous knowledge of forces and use them here for torques. All right, so we're going to see 6 different examples of a very simple system. And what we're going to do is calculate the torque. We're not really going to worry about this direction piece per se right now. We're really going to look for the magnitudes of the torques, but we are going to have a little bit of a discussion on which way the system should rotate. Next time we're in class and we can do this all together, we're going to discuss the right-hand rule, and that'll give us a much better tool at talking about and finding directions, but that can wait for a little bit later. So we're going to have 6 different situations. In all of the situations, we're going to apply the exact same force, F, and each situation is going to have the exact same object of the exact same size. So they're all going to be of length 4 meters, and they're giving us that the force applied has a magnitude of 10 newtons. So let's look at the first case. All right, in this first case, what we have is a rod that's going to be held in place right here at that origin point O. So what that point is going to be is our axis of rotation. It's a really good idea to start thinking about where that point is going to be when we're looking at torque problems, so that we can next figure out what our lever arm is going to be. I know here that the force applied is perpendicular to my rod. They've given me an angle there of 90 degrees. Whenever we solve any problem, first couple steps are usually going to be about the same. Let's draw out a picture, which we already have here. Let's label our quantities, let's list our variables, and then we're going to write out our equation. The one thing that this picture is missing, it does have my force, but it doesn't have our lever arm drawn. So we know that the lever arm is going to be the distance between the axis of rotation and the force applied. So I'm going to go ahead and draw that right here in purple. It might be a little bit hard to see, so I'm going to double up on that line. That right there will be our lever arm vector. I'll label it R. And now I'm going to list all of our knowns. So for example, we know that our lever arm R, because it goes from one end of the rod to the other end of the rod, is going to be the full length of the rod, which is 4 meters. I know what the magnitude of the force is. They've given that to me as 10 newtons. Another useful piece of information that they gave me is the angle between, and if I look at the picture, it's an angle between our lever arm and our force, which is really good because that's exactly the angle that we need in our formula for torque. So that's given to us as 90 degrees. The next thing I'm going to do is write out our unknowns. So those are the things that we do know. What we don't know and what we'd like to find out is the torque. All right, our next step is to write out our equation. So we know that torque equals RF sine theta. And I'm going to plug in my, my knowns into my equation. Torque will be R, which is 4 meters, times F, which is 10 newtons, times sine of the angle between them, which is 90 degrees. Now sine of 90 is a really nice value. That's going to give us 1. So 4 times 10 is 40. 40 times 1 is 40. So the magnitude of this will be 40. Now our units. You can write this in any order, but in general, we write them as Newton meters. So our answer here for our magnitude of the torque would be 40 Newton meters. Now in terms of the direction, if I were to look at this system, what I like to do sometimes is mimic it. So I'll put my pencil down on the desk, I'll hold it at the same point, and I'll apply the force in the same direction. And what I'll see is that this system is going to end up rotating counterclockwise. So the direction of this, if we remember back when we were doing uniform circular motion, that counterclockwise is positive and clockwise is negative. So the way that we would describe our direction is by leaving this value positive, because torque is a vector quantity. So the sign that's in front of the number is going to give us our direction. So this answer right here, 40 Newton meters, gives us both the magnitude, which is 40, and the direction, which is positive, so counterclockwise. All right, so that's our first example. It's a pretty straightforward. We're going to run through another 5 a little bit quicker, and we're going to see a couple different ones. All right, here's our second example. I've already drawn the lever arm, which is the distance from the origin here to the force vector at the other end. It's a really terrible looking arrow, but I'm not an artist, I'm a physicist. Sorry, guys. I've also written out our knowns. We know that the lever arm, again, is going to be 4 meters because it goes the whole length of the rod. The force still has a magnitude of 10 newtons. What's different in this one is that the angle between the lever arm and the force is 120 degrees. Finding the torque, again, all I'm going to do is plug right back into our formula, RF sine theta. In this case, my R is still 4, my F is still 10 newtons, my sine of 120. Now this one is going to be a little bit tricky. your calculator, depending on the calculator that you have and the mode that it's in, will either give you a value like 0.866 for sine of 120. It's square root 3 over 2. I don't care which form you have your answer in. It's all the same to me. But when I multiply these numbers together, what I'm going to end up getting is either 20 square root 3 Newton meters, if your calculator leaves it in its exact form, or if it's not exact but approximates, it'll be about 34.6 Newton meters. I'll accept either answer. They're both perfectly fine. A couple of things to notice. Number one, this answer is smaller than our previous answer. Our previous answer was 40 Newton meters. Well, that's because this sine theta piece here limits how big our torque can be. The biggest possible value that sine can ever have is 1, and that happens at 90 degrees. So anytime that you're not at 90 degrees, you're actually getting less torque. That's one major thing. The other thing is with direction. If I were to do this system the same way that we set it up last time, putting your pencil on the desk and pushing it in the same direction, applying the same force, this is still going to rotate counterclockwise. So our answer is still going to be positive. Okay, another example really quickly. Our force has changed. I've drawn the lever arm again from the origin or the axis of rotation, which is still this point O right there. The rod is fixed at that point. It's stuck there. And I've drawn our lever arm from the axis of rotation to the point where the force is applied. That's this purple vector right there. I've listed out our variables again. Our R and our F are still exactly the same. Our theta has changed. And again, all I'm going to do, plug right back into our formula. This should start feeling pretty routine at this point. Our lever arm is 4 meters. Our force is 10 newtons. Sine of 30 degrees is 1/2. So 1/2 times 40, this will end up giving me a torque of 20 Newton meters. And our trend that we started noticing in the last problem is continuing. The smaller my angle is getting, originally it was originally it was 90 degrees, I'm sorry. The smaller our angle is getting, the smaller our torque is getting. The closer and closer my angle gets to 0, the closer and closer sine is going to get to 0, and the closer my torque is going to get to 0. Now, I do understand that 120 is bigger technically than 90 degrees, but 120 is the same angle as... So sine of 120 will give us the same as sine of 60. And 60 is smaller than 90. And 30 is smaller than 60. So our trend is holding pretty strong. The smaller our angle, the smaller the torque is going to end up being. Now let's take a look at another one. Now this one's going to look a little bit different than the others. The first thing we're going to notice is that this force is now pointing down instead of up. What that should lead us, to feel that our first, gut reaction is to say that the rotation is now going to be opposite. Before we saw that our up push produced a kind of counterclockwise rotation, and it would be natural for us to assume that this down push will do the exact opposite. And in this case, this is going to be true because we're still pushing on the same side. Be careful with this kind of thinking for other types of rotations because it depends on where you are and how you're pushing. In this case, it works out really well. The second major thing that we're going to notice is that the force is no longer being applied in the same place. In the other problems, we saw that the force was at the very end of the rod, the full length. In this problem, we're going to see that the force is actually 2 meters away from the end of the rod. Well, the rod in total is 4 meters, so if I'm 2 meters away from the edge, I'm at the very center. What that means is when I draw my lever arm, which is going to go from my axis of rotation to where my force is applied, this guy right here, my lever arm is no longer going to be 4 meters. Instead, it's going to be 2 meters. Now, the angle between my lever arm R and my force vector F is given to me here as 60 degrees. So I'm going to fill that in on my table over here with my knowns and my unknowns. And now I'm just going to solve exactly the same way that we've been doing. I'm going to start by writing our formula. Torque equals Rf sine theta. And then I'm going to plug in my knowns into the formula. So torque equals 2 meters times 10 newtons times sine of 60 degrees. Well, 2 meters times 10 newtons is 20 newton meters, and sine of 60 is square root 3 over 2. So our answer could be 10 square root 3 newton meters if you'd like, or if your calculator will give you values that are approximate decimal values and not exact values, you'll get something close to, I think, 17.3 newton meters. So there's our magnitude. Now our direction, this thing is going to rotate in a clockwise direction, and clockwise is negative. So our direction will actually have, or our answer, will actually have a negative sign to show that this thing is rotating in the negative direction, which is clockwise. Now, this is our second to last one, and this one and the next one are going to be very, very similar, so I'm going to leave them both up together as soon as we finish this one. This one is going to be a little bit different than the ones we've seen, and the first thing we should notice is where that force is applied. If you take a look at this, you're going to see that it is pushing against the axis of rotation. So this tells us a couple things. Number one, what this tells us is that the distance between the axis of rotation and the applied force, in other words, the lever arm, this R value, is going to end up being 0 because it is pushing on the axis of rotation. And that's going to be huge, because if I look at the formula for torque, tau equals Rf sine theta. Whoops, there we go. That's a terrible theta, I'm sorry guys. I just made it worse, oh well. If I look at this formula, it's straight up multiplication. And we know that if we take any number, any quantity actually, and we multiply it by 0, what we're going to end up getting as a result is 0. So if I plug this in, and they did give us an angle, so I'll put that in my table here, 60 degrees. If I were to plug this in, tau equals 0 meters times 10 newtons times sine of 60 degrees. Well, sine of 60 is square root 3 over 2. Square root 3 over 2 times 10 is 5 square root 3. But none of that matters, because when I multiply it by 0, what I'm going to end up getting is 0. And this is really, really important, because this gives us a really important condition for torques. And what that is that any force that acts on or passes through, well, actually, I don't have enough data for that part. So let's stay with our first claim that acts on, and I can't seem to get all of these marks gone. I'm sorry, Geo. So any force that acts on the axis of rotation will produce no torque. What that means is that this force could produce a translation. It could get this system to move in space, either in the X, the Y, or the Z direction. So up, down, left, right, forwards, backwards, something like that, linear motion. But it won't be able to produce any type of rotational changes. It won't actually make this thing spin either clockwise or counterclockwise. And this is really nice because sometimes we can get some very complicated looking problems, and being clever with our choices of axis of rotation could eliminate a lot of the torques that we've got. Our next example is going to look very, very similar to this one. I'm going to put it up right now. All right, this is our last example of these types of problems. And if I take a look at this guy, I'm going to see that my force applied over here is not acting at the origin or at the axis of rotation, which is good. There is going to be a lever arm between my axis of rotation here and where my force is applied. So that's one difference that this one has over the last one. But the angle between my lever arm and my force is going to end up being 0 or 180 degrees. They're both fine. They're both the same. And what that means is when I list out my variables, here's my lever arm, my force, my angle. When I plug into my formula for torque, tau equals RF sine theta, when I plug in 0 for theta, I'm going to end up getting 0. And just like in the last problem, anything times 0 is 0. On top of that, if we remember our line of action definition, I could make a line that passes through my force, and I could move that force anywhere on this line, and I could actually put it right on top of my axis of rotation. And that would look exactly like the last problem. So what I'm going to do is take a look at that claim that I made a second ago, the one that's right above us, that says any force that acts on the axis of rotation will produce no torque. And I'm going to add not just acts on, but also passes through the axis of rotation will produce no torque. So neither of these examples are going to be able to produce any type of rotation. They could still produce translations, but that isn't a torque quantity. That would be something from chapter 4 when we do Newton's laws or the sum of forces, and we have linear systems, which is not what we're going to look at. These are just rotations. So these two examples are the most common examples where we will produce no torque at all. If you are acting on the axis of rotation or if you are passing through the axis of rotation. All right, so we're going to do a pretty straightforward example problem of a just torque type of problem. All they're going to ask us to find is the magnitude and the direction of the torque. And then they're going to ask us something that seems a little bit intimidating, but isn't that bad. We already talked about it in the last couple problems. So they tell us that a machinist is using a wrench to loosen a nut. The wrench is 25 centimeters long, and he exerts a 17 Newton force at the end of the handle at 37 degrees relative to the handle. They gave us a picture, so that's nice. We don't have to draw it. Otherwise, we would have had to draw something, make our lives much easier. What they're asking us to find is what torque does the machinist exert about the center of the nut. So what is the magnitude of the torque that this force is going to produce in this situation? They did give us a picture. What they didn't include in this picture is the lever arm, or where the axis is. Well, the first part is to figure out the axis, and that's going to be pretty easy and straightforward. That piece right there, the center of the nut, is going to be the axis of rotation. That's going to be about which all of this thing is going to rotate. So our lever arm is going to start there, and it's going to go up until the point where the force is applied, which is at the end of the wrench. So it's going to go from here, and it should be a straight line, but again, I am a terrible artist, so I'm hoping you guys can at least kind of see the vector that I'm drawing over here, even though for some reason on my picture it keeps disappearing. I'm not really sure why it does that. Let me try it again. Nope, it keeps disappearing. Well, hopefully you can see that it goes from that center nut all the way down over here to where the force is applied. Let's list out our variables. We know R is our lever arm, and that's going to be the 25 centimeters that it goes from the nut to the end of the wrench. Now 25 centimeters is not exactly the unit that we want to use. The SI unit for distances are meters, and we know that centi means hundredth, so there are 100 centimeters in a meter, so this is going to be 0.25 meters. The force is 17 newtons, and the angle between my lever arm and my applied force, if you could have seen the picture or the vector that I was drawing, I'll draw it again really quickly and hope it doesn't disappear too fast. The angle between that purple line that I'm drawing and the angle, the force vector, is 37 degrees. So what they want us to find is tau, the torque. All right, I've listed my variables. I'm going to write out my formula. Tau equals RF sine theta, and I'm just going to fill out my my equation. What happened to my video? Ah, okay. All right, plugging in our variables, we're going to get 0.25 meters times 17 newtons times sine of 37 degrees. So we can plug all of this legitimately ugly stuff in the calculator, and what we're going to end up getting is something close to 2.557. So we can round that to about 2.56 Newton meters. Now we can look at this system and kind of visualize, and we can see really quickly that this is going to rotate in the counterclockwise direction, so it's going to be a positive number. So I'm going to leave this number as positive, and I'm going to say that my answer is 2.56 Newton meters, direction and magnitude. That's good. That part's easy. Looking at part B, what is the maximum torque that this person could exert with this amount of force, and how should that be orientated? Well, we saw in the last couple examples that we produced the most amount of torque when the angle between the torque vector and the force vector was 90 degrees. And that's always going to be true. The maximum amount of torque will always be produced when the angle between the lever arm and the force is 90 degrees. So the way that we would write something that looks like that would look like this. So the max torque happens when the lever arm R and the force vector F are perpendicular. Now it asks us to find that maximum value. Our lever arm stays the same, and our force value is going to stay the same. What will change a little bit is our angle. So to find the maximum part for part B, our lever arm is still going to be 2.5 meters, or 0.25, sorry. Our force is still going to be 17 newtons, but now our angle is 90 degrees. So when we go to plug in, tau equals RF sine theta, 0.25 meters is R, 17 newtons is F, and sine of 90 degrees is 1. What we're going to end up getting is a quarter of 17, or 4.25 Newton meters. So the maximum amount of torque that you can produce in this situation would be about 4.25 Newton meters. How would this thing need to be orientated? Well, this force vector would need to be pointing at a 90-degree angle like this relative to our lever arm. That's how it would need to be orientated. Let's take a look at one more example, and we're going to see how we can apply the ideas from Newton's laws and the general concept of what net means with torques. All right, so here is our last example problem for now. It says to calculate the net torque about the point O for the two forces applied in the figure. The rod and both forces are in the plane of the page. That part doesn't really matter. It's just telling us that they're all in line. That's okay with us. A couple important things to notice. Here is that really important word net. Huge word for us. The word net means total or sum, which means we're going to be doing sums. We're just going to be adding them up. Now the point O, that point right there, is our axis of rotation. These two forces are going to make this rod system rotate around that point O. So I'm going to do this in two columns because I've got these two forces. I'm going to look at force 1, and then I'm going to look at force 2. For force 1, I'm just going to make our table of our knowns and our unknowns. We know what the magnitude of the force is. They told us that's 8 newtons. Again, the magnitude of the force. I know that this force is pointing downwards, so the vector should be negative, But when we're looking at the torque, we only want the magnitude, the absolute value of the force. Our lever arm R is going to go from the axis of rotation, so from the O point, and go all the way over here to the end of the rod. That's going to be 2 plus 3, which is 5 meters. And our angle theta between our lever arm and our force for force 1 is 90 degrees. What we're looking for is our torque, tau. So I've listed my unknowns and my knowns. Our next step is to write out our formula. So torque equals RF sine theta. And then we're going to plug in our knowns into our equation. So tau equals our lever arm is 5 meters. Our force vector is 8 newtons. And our angle is 90 degrees, sine of 90. 5 times 8 should give us 40. 40 times sine of 90, which is 1, is going to give us 40 Newton meters. So there's our magnitude of the torque. Now in this case, this system, if I look at this force, and again, I put my pencil down on the desk and I hold it on the left edge and I push it in the same direction that that picture is showing, this thing is going to rotate clockwise. That force is going to produce a clockwise rotation. And clockwise is negative. So this will produce a negative 40 Newton meter torque. Now notice that when I did this, I completely ignored force 2. I don't care about force 2 right now. All I care about is what force 1 would do. And I'm going to do the same thing with force 2. I'm going to ignore force 1, and I'm just going to calculate what force 2 would do if it was by itself. So I'm going to list out the force over here on the other side of the column. They told us that's 12 newtons. I'm going to list out our lever arm. I'm going to draw a new one actually over here in my picture, and that's going to go from my origin O over here to my force 2. I'll call that R2, and that's going to be 2 meters. And the angle between these two, they told us, is 30 degrees. And again, I'm looking for tau. So I'm going to write in our formula. Tau equals RF sine theta. Again, I'm sorry guys, my R's are really bad. It's a bad habit of mine. I'm going to plug in all my knowns. Tau equals 2 meters times 12 newtons times sine of 30 degrees. 2 meters times 12 newtons is 24 Newton meters. And sine of 30 is 1/2. 24 times 1/2 is 12 Newton meters. Now this force, if I do the same thing with my pencil, will create a counterclockwise rotation, so it's going to stay a positive number. So I'm going to leave it as a positive 12 Newton meters. Now I haven't actually found the net torque. What I have found are the two individual torques. In order to find the net torque, what I need to do is sum the torques. And again, it's just addition. Now I have two forces, and these two forces have produced two torques, so I should have two terms in my sum. And it doesn't really matter the order that you do them in. I'm going to start with, torque 1 and then torque 2. So this will be torque 1 plus torque 2. Now torque 1 is negative 40 Newton meters. This thing right here, that's torque 1. And torque 2 is 12 Newton meters. So this whole thing right here is torque 2. And when I take negative 40 plus 12, I'm going to end up getting 28, negative 28 Newton meters as my net torque. There's my answer for my net torque. What does this mean? Well, it means that in general, in the end, this thing is going to end up rotating clockwise, because my answer is still negative, with 28 Newton meters of torque. All right, so we've seen a couple examples. We've worked out some torque problems. We've seen how to find net torques. The Mastering Physics is going to have a couple problems on finding individual torques, and probably a couple problems on finding the net torques.